Okay, I'd say I'd like to do the last couple in one more video, but with the way I talk, it's likely that won't happen, but bear with me. So, oh yeah, it's not going to happen. So we have the function x squared minus 3x minus 4 over x squared minus x minus 6. So a rational expression. Called a rational expression, as you hopefully remember, rational numbers are numbers that are fractions of integers, so they're fractions of nice things. Polynomials are nice things, so fractions of nice things are rational equations. Anything that can be written as a polynomial over a polynomial is a rational expression. And they do have, some very common aspects to their graph. The simplest full rational expression is good old 1 over x. And if you look at the graph of 1 over x, it does have that very particular rational look. It has a horizontal asymptote, it has a vertical asymptote. These are common aspects of rational functions. They don't always exist in rational functions, but they are certainly super duper common, if I may be allowed to use the term super duper. So there are several things that we should be able to find in a rational function. We should be able to find x-intercepts, y-intercepts. We should be able to find vertical asymptotes. We should be able to find horizontal or slant asymptotes. You can have either horizontal or slant or neither. You can never have both. If you have a horizontal asymptote, you can't have a slant asymptote. If you have a slant asymptote, you can't have a horizontal asymptote. But it is possible to have neither. These are often referred to as end behavior asymptotes to kind of link them together. Now, this is not the order you're asked in this particular question, just to be clear. In this question, vertical asymptotes was number 9. Horizontal slant asymptotes was number 10. Y-intercepts was 11. And x-intercepts, number 12, asked you for the zeros, so that's actually number 12. But it really doesn't matter what order you do these in. It's up to you. So do them in whatever order you feel, and then at the end, draw a nice graph. So, x-intercepts. In general, anytime you're trying to find an x-intercept, you find x-intercepts by letting the function equal 0. Let the y equal 0. So if we let this whole thing equal 0, well, fractions equal 0 when their numerators equal to 0. So if you want to find x-intercepts, let your numerator be 0. Just let the x squared minus 3x minus 4 equal 0. When your numerator is 0 and your denominator is not 0, the whole fraction turns into a 0. 0 over 5 is 0, 0 over 7 is 0, 0 over almost anything except 0 is 0. So if we knew what made the top 0, we'd have a good sense of where our x-intercept should be. The nice thing is, hopefully this is nicely factorable. We got, a 4, it's a negative 4 and a positive 1. All right. Yep. Equals 0. So that equals 0 at negative 1 and 4. So these are possible x-intercepts. I said you get 0 when the top is 0 and the bottom isn't 0. So if the denominator became 0 at x equals 4, we'd have to throw it out. Your book talks about that. It's where it talks about having holes instead of asymptotes. So do be sure you look at that. And we'll talk about that when we get to asymptotes. So that's x-intercepts. You guys know how to solve that stuff. Not a big deal. Just remember to do it. That's what an x-intercept means. Set the whole thing equal to 0. Ignore the denominator. Just find the numerator and check on your values later. Y-intercepts. You find x-intercepts by letting the whole function be 0. You find y-intercepts by letting x equal 0. Every y-intercept has an x value of 0. That's why it's on the x-axis. So we're essentially just finding f at 0. Plug in a 0. It's 0 minus 3 times 0 minus 4 over 0 squared minus 0 minus 6. All this stuff goes away, doesn't matter, blah, 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 blah. -4 over -6, if you prefer, reduces to 2/3. So your y-intercept is 0.02. Just plug in the 0, find the value, that's your y-intercept. It's happened sometimes that the denominator will turn to a 0. That's undefined, means you don't have a y-intercept. Happens up here, there's no y-intercept in this. At 0, it's 1 over 0, undefined. If your numerator ends up being 0, okay, then your y-intercept is 0. If your y and x-intercept are 0, fine. That means you have a intercept at the origin. That happens, don't let it throw you off. How's my time? Oh, good. Vertical asymptotes are nice to find next. Some people like to find vertical asymptotes right after the x-intercepts because it's nice to compare them. That's okay, as I said, whatever order you like. Vertical asymptotes happen where the function is undefined. The function is undefined whenever we divide by 0. So we're going to take that denominator, the x squared minus x minus 6, figure out where it's 0. Where it's 0, this thing is undefined, and we might have a vertical asymptote. Again, this is nicely factorable. These problems are not chosen to be nasty. They're chosen to go through your tools. So sometimes they're not factorable. I'll do that sometimes, but they're usually never horrible. So don't fight with them too much. But we get x equals -2 and x equals 3. So those are our possible vertical asymptotes. Those lines, the line x equals 3 and the line x equals -2. And what we want to check is to see if any of these numbers are the same as our x-intercepts. Because if it's both an x-intercept and a vertical asymptote, they cancel each other out. That means the factor is existing in both, and they would essentially divide each other out, leaving, instead of an asymptote, a hole. So make sure you look at that section on holes. Here, none of them match up. -1, 4, -2 and 3. They're all unique. So these make our actual x-intercepts, and these make our actual vertical asymptotes. So where does that put us? If we start looking at our graph here, we had x-intercepts at -1, 0 and 4, 0. We have a y-intercept at 0, 2/3. Make sure you give these to me as coordinates or I get grouchy. Your vertical asymptotes are occurring at the line x equals -2 and the line x equals 3. Again, be sure to give those as lines. Vertical lines have that form, x equals a. So be sure you're doing that. Hopefully that's not too glossy on you. If it is, let me know. So we could start plotting some of these things. So 1, 2, 3, 4, 5, 1, 2, 3, that's our x. 1, 2, 3, 4, 5, 1, 2, 3, and that's -5, 5. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So x-intercept at -1, 0. So x-intercept right there. X-intercept at 4, 0. 1, 2, 3, 4, 0 right there. Vertical asymptote, the line y equals -2. Oh, sorry, x equals -2. That's the line x equals -2. All points where x is -2. X equals 3, right next to there. X equals 3. And y-intercept at 2/3, so 2/3, so partway through there. So y-intercept at 2/3. Okay, great, got a bunch of points, a couple asymptotes. The last thing we have to find is that end behavior asymptote. End behavior asymptote, the horizontal or slant asymptote. So let's remind ourselves what our function is here. F of x equals x squared minus 3x minus 4 over x squared minus x minus 6. Now, again, I'm assuming you've read through the section and played with a little bit of these. So you're familiar with the idea of horizontal and slant asymptotes. The nice thing about finding particularly horizontal asymptotes is there really isn't a lot of work involved. It's really just an observation. The trouble with that is you have to be able to make the observation. Because these are end behavior asymptotes, they're really asking what happens to the function as we travel far in the x positive or far in the x negative. What happens as we get towards the outside, the ends. So we're really essentially imagining what happens to this for very large values of x, either very large positive or very large negative numbers. Now you can imagine if you put in a value like x equals 1,000, between 1,000 squared and 3,000, the fact that we're subtracting 4 or 6 really stops making all that much of a difference in our number. So when you're trying to figure out what the end behavior is, those numbers really aren't doing anything. Even the difference between 1,000 squared. 1,000 squared is a million. The fact that you're adding 3,000 or subtracting 1,000 or subtracting 3,000, you're still up in the millions. Those numbers really aren't affecting you. Really, the only thing that's affecting your outcomes when you have very, very large numbers are your lead terms. So when you're dealing with finding end behavior, horizontal particularly, but even slant asymptotes, you're really comparing the size and strength of the lead terms. If they are the same degree, if your book says m and n for the degrees of the top and the degrees of the bottom, I always like just, simplify it. If the top is the same as the bottom in terms of degrees, then we're going to have a horizontal asymptote. If the top is bigger than the bottom, you're not going to have a horizontal asymptote, because if the top is bigger, you put in bigger numbers, that top is going to just become larger and larger and larger. The difference between 1,000 to the third and 1,000 squared is the difference between a million and a billion. This thing is, if the top has a larger power, it's just going to get so huge, your graph is going to go off and off and off and off. If the bottom is larger, say this was x squared over x to the fifth, again, if we're thinking about large x's, 100 squared is 10,000. 100 to the fifth is that 10 billion? Yeah, I think it's 10 billion. 10,000 over 10 billion is a very, very small number. If you have a really big denominator and a comparatively small numerator, you're going to head towards zero. So all of that logic that your book talks about the m's and n's, is really talking about how those things compare. So if the bottom is really small and the top is really big, really small bottom, really big top, bottom smaller than top, then those things are the same, sorry. If the bottom is smaller than the top is winning, the top takes over, the top gets bigger faster, you're going to have no horizontal asymptote. If the bottom is larger than the top, then the bottom is going to be big. The bottom's going to win. The denominator is going to get larger and larger, while the numerator stays comparatively small, giving you numbers like 10 1/millionths, 100 10 billionths, really small values. You get that horizontal asymptote at y equals 0. This thing levels off. As the inputs get larger and larger, it gets closer and closer and closer and closer to 0, giving you that nice horizontal asymptote at y equals 0. But if they match, as they do in this problem, this is essentially going to become like a billion over a billion, 10 billion over 10 billion, a trillion over a trillion. Yeah, there's going to be some little variations, but as those numbers get larger and larger, you're essentially going to have the same number on top as you have on the bottom. And when that happens, this thing approaches 1. Now, if this was 3x squared over x squared, then yeah, it'd be like 3 million and 1 million, giving you 3 over 1, be the horizontal asymptote of 3. If this was a 3 and that was a 5, you'd have like 3 million over 5 million, which essentially reduces to 3/5. 3 billion over 5 billion reduces to 3/5. 3 trillion over 5 trillion reduces to 3/5. So anytime they're the same, it ends up being the ratio of the lead coefficients. In this particular problem, they're both 1s, so we have a horizontal asymptote at y equals 1. Now that was a very quick version of the whole asymptote logic. Your book does go through it, but you'll look back through it and kind of try to put it in those contexts and see if that makes sense. So because the degrees match, we have a horizontal asymptote at the ratio of the lead coefficients. 1 over 1 is 1. So we have a nice horizontal asymptote here at 1. Make sure you review that. I did that very quickly. By the way, slant asymptotes happen when there is no horizontal asymptote and the bottom is less than the top, but only by 1. If the degree of the bottom plus 1 is equal to the top, like a 3rd degree over a 2nd degree, or a 4th degree over a 3rd degree, even a 7th degree over a 6th degree, if it's only off by 1, you get a slant asymptote. You find that slant asymptote by performing the polynomial long division. There are examples of that in your text. Be sure to look at them. Very, very important. Okay. Now, just real quick, we have to draw the graph here. I've got a couple minutes, so we can take some time here. Now, as you may remember from our original example, the graph of 1 over x, rationals very commonly have these kind of sweeps in them. So really our goal is to figure out where those sweeps have to be. And you can kind of imagine that these horizontal asymptotes, the vertical asymptotes, break us into kind of 3 sections. We've got this section here. We've got this section here. And we've got this section here. So in each of those sections, we have to figure out where these kind of sweeps are. It's actually not as hard as you might think. The text is very good at suggesting that you pick test points. Like if you want to know where the graph is at 5, whether it's up here or down here, well, plug in x equals 5. Oh, excuse me. Plug in x equals 5 and you'll get a value. That value will tell you where to plot. So that can be a nice way if you're unsure. But actually, you generally don't have to do too much of that. If we look in this pink section, we've got 2 choices. Either that sweep lives up here, or it lives down here. The problem is it has to go through this x-intercept at 4. So it can't be up here. If it's up here, it would have to be asymptotic to this, asymptotic to the 1, and it wouldn't pass through this point. The only way for it to happily pass through that x-intercept is for it to come up from the bottom and then through that asymptote. So we could plot some points to make sure that's true, but it really has to be. Even if you wanted to say, well, what if it came down and passed through? Well, okay, if it came down and passed through, to end up being asymptotic to this y equals 1, it would have to come back up and pass through. And if it came back up, it would have to have another x-intercept, and it doesn't. So this is the only time it can pass through, so that's got to be where it is. Similarly, over here, it's either up above or down below. If it was down below, it would have to have an x-intercept, and there are no x-intercepts over here. We know the only 2 x-intercepts. So it can't be down here. It has to exist up here. So we can draw it in. So that's good. We have a lot of information from where our x-intercepts are. We even have a lot of information for where they aren't. There are no x-intercepts here. It can't go through. These can be a little tougher, but notice we know that the curve has to go between those. And we know it doesn't curve back up afterward because there's no other x-intercept, so it has to come down this way and up through those. The big question is then what does it do? Well, again, you might want it to not hit that asymptote, so you might want to curve back down. But again, if you curve back down, you'd have to have an x-intercept. There's no x-intercept for us to pass through. So it must continue upward. Now, a lot of people shout at that. I can almost hear you right now, but you can't pass through the asymptote. Sure you can. You can pass through horizontal asymptotes. You're right, you can't pass through vertical asymptotes. But horizontal asymptotes tell you about end behavior. This isn't an end behavior argument. It's a nice little vertical asymptote. Sorry, it's a nice little horizontal asymptote, right? What happens in the middle? We can be equal to 1. The horizontal asymptotes are end behavior arguments, not vertical arguments. So without plotting a lot of extra points, you can often get a very nice sketch for your graph. When in doubt, though, plot some points. You want to know, like if you're unsure, like you want it to come back down, stick in, was that 1, 2? Stick in x equals 2. I think that's x equals 3. Anyway, stick in x equals 2 or 3, plug it in, and you'll see you'll get something above 1. Okay, it's got to go up. Great. Okay, I'm over my time. Hopefully that doesn't cause me too much trouble. If it does, I'll just make another video. But work with these, play with these. This is a nice place to get a whole bunch of points, and it's a kind of a horrible place to lose a bunch of points. If you practice this whole thing out, a handful of times, you can get fairly good at it and not lose points here. Don't try to use this as a place to make up points, not lose them. Okay, one video left.